and welcome to the new session of the video, that is the standard reduction formula and its uses in decomposing a set of reducible representation as the sum of irreducible components. I am your instructor, Saurabh Muktibodh, and let's have a look over the subject. First thing that we are trying to use is the standard reduction formula. Decomposition of a reduction representation in terms of irreducible representation is done by a method that is known as the standard reduction formula. In its simplest form, it can be described as AI is equal to 1 upon H summation of chi I r into chi j r, where AI is the number of times the ith irreducible representation is present in that particular reducible representation. The summation is carried out over all the symmetry operations of the group of order H, and chi I r and chi j are the characters of the operation of R in a reducible and irreducible representation respectively. So that helps us in deciding the reducible representation can be decomposed into the sum of the irreducible components. And if you take an example, just start with the water molecule and just believe that all the three atoms are decomposed into the Cartesian coordinate axis x, y, z. That would be very useful in vibrational spectroscopy, and just obtain a basis for a reducible representation as under identity C2 sigma xz and sigma yz for C2V point group. Now, if we go through the character table of C2V point group, we find that 9 minus 1, 1 and 3, which are formed by the assuming every atom to be seen in XYZ format, basis functions have been generated, and they are obviously a reducible representation as they do not belong to any of the irreducible component that has been described in the character table. So it is obvious that 9 minus 1, 1 and 3 makes a reducible representation. But then, because it is the irreducible representation that are of fundamental importance, I would say that it is important for us to decompose this reducible as the summation of the irreducible components. And to get it done, what we will do is, we'll take the help of the C2V character table. Now, the decomposition formula can be used. Just multiply the order of the group 1 by 4, that is order of the group, the character of identity in a reducible and character of identity in an irreducible set, added by the character of C2 in a reducible multiplied by character of C2 in an irreducible component. Similarly, the third one, the character of sigma xz in a reducible and character of sigma xz in an irreducible set, and so on. So the character of yz in a reducible representation and the character of yz in an irreducible representation, that would give this all summation, and this would give the number of times that operation has come out. So just look at this. This is not equal to 1 as shown here. This is, now we'll try for the first thing, a1. So a1 is equal to 1 by 4. Just look at here. Now when you look at this point, you see that this is 9, 1. So 9 into 1 is 1. Similarly, minus 1 and 1 and 1, that is the three things, so that is minus 1. 1 into 1 into 1, that is plus 1. So you have multiplying here 1 and 1, that is plus 1. And now 3 into 1, that makes it 3. And if you sum them up, you find that it comes the total of 3. That means this A1 has 3 times occurred in that reducible representation. Now just go for the next one, A2. Now A2, how many times A2 has appeared in that expression? We'll find out. Again 1 by 4. 9 into 1, that makes it 9. Minus 1 into 1, that makes it minus 1. 1 into minus 1, that makes it minus 1 again. And 3 into minus 1, that makes it minus 3. So if you add them up, that will give a total of 1. So the conclusion is A2 has come once in that reducible representation. Now A3, for A3 third representation, we are assuming that it is for B1. So it is equal to 1 by 4, 9 into 1, that is 9, minus 1 into minus 1, that becomes plus 1. 1 into 1, that is again plus 1. And 3 into minus 1, that becomes minus 3. That gives a total of 2. So B1 has appeared twice in that reducible set. Let's talk about B2. So that is 4A4 here. I will talk about B2. So 9 into 1 is 9. Minus 1 into minus 1, that is plus 1. Then 1 into minus 1, that is minus 1. And 3 into 1, that is plus 3. And that gives a total of 3. So the conclusion that we can draw is that the tau reducible has to have this kind of shape: 3A1 plus A2 plus 2B1 plus 3B2. And that is very important when you are using the vibrational spectroscopy for giving some theoretical basis to bond movements. Taking another example, let us have a point group of C3b. This is the point group of C3b, and now we want to sum over the A1, A2, and E. Just keep on doing the summation. So 1 plus 1 plus 2, that is 4. Now 1 plus 1 is 2, 2 minus 1 is 1. Now 1 minus 1 is 0, and this is 0. Now that I have seen that the summation has yielded 410. So I can say that this tau summation should be equal to A1 plus A2 plus E, because I have done this deliberately. Now I had to prove that this is so. So again, we'll use the standard deduction formula to obtain the corresponding irreducible components into the reducible set. So let's again begin. Let's start with A1. How many times A1 has come? Now just look at 1 plus 2 and plus 3, that is 6. So order of the group is 6. So 1 by 6. Now multiply 4 into 1 because E is once only. So it's 4 plus. Now 1 into 2, because there are 2 elements in the class. So that is equal to 2. And 0 plus 1 into 3, obviously that's going to be 0. And that will finally give something which yield 1. So A1 has appeared once in the entire tau sum. If you go for A2, now for A2 you will have 4 into 1 into 1 and 1, 1 and 2. So 1, 1 and 2. 0 minus 1 and 3, well, of course 0 multiplied by any number is going to be 0. So this expression is going to give you a result 1. Let's talk about E. How many times E has come in a reducible set of representation? 1 by 6. 4 into 2 into 1, that is 8. 1 into minus 1 into 2, that is minus 2. And 0 multiplied by 0 and other things is going to be 0. So you have 8 minus 2, that is 6, and 6 by 6 is equal to 1. Now what we see is A1 has come once, A2 has come once, and E also has come once in this set of representation, which we have derived deliberately. That is confirming that tau sum is equal to A1 plus A2 plus E. So this is the beauty of the standard reduction formula, that it allows us to determine a reducible representation as the sum of the irreducible representations for a particular character table in a particular point group. And the reducible representations can be generated by assuming any logical set of conditions or bases that can be useful even in bonding, in spectroscopy, quantum mechanics, in splitting of orbitals, etc. So this formula is of great use, and once we understand it, we are going to use it quickly whenever it is required. So thanks for watching. Indeed, see you in the next video.